I do this? Well, first thing I do is say, well, what does a cumulative distribution function look like? Okay, well, the first thing is it's going to have, well, how many, at the moment this is a piecewise function with two sections, right? It's defined to be a half sine x between 0 and pi and 0 everywhere else. So when I define my cumulative distribution function, I've got to define it for all the sections that are possible, right? So first of all, I define my cumulative distribution function with a capital because it's got to do with integral, because it's how I calculate probabilities, okay? And if I think about this one for a start, there's actually three sections to define. What are they? What are the three sections that this graph defines, or this function defines? Give me any of them. Give me one. 0 to pi? Yep, so there's a section of my graph over there. Remember the two red dots that I drew? There's a section of the graph that's from 0 to pi. And I need to work out, well, what is that function going to be? So I'm going to replace that with an actual equation in a minute, okay? What are the other two possible values for x? There's not two individual, but two ranges of values. Less than what? Less than 0 and greater than pi. Yeah? So I'm going to so x could also be less than 0 and x can be greater than pi. So what is my function when x is less than 0 going to be equal to? So what's the value of my function out here? 0. And what's it out here? 0. Because it can't be out there, right? So for those two, I'm going to have 0 there and 0 there, because they're not defined out there. So all I need to do is work out, well, what's this equation going to be here? Okay? And basically what I want to try and do is work out, well, what is the equation, that map, that will get me my probability from here to there? Okay? And the way I do that is say, all right, well, I'm going to identify a variable. So I've actually started to do it over here. Okay? So you can see here's the working that oh, no, you can't. I'm drawing all this and you can see nothing. Why doesn't someone say something?
Well, I thought you were doing this all.
No. There we go. Look at that. See, that's what I was drawing before. Look at that. I was actually writing and no one was saying a word. Okay, so this is what I've got so far, right? So the way I work out my f of x is say, right, well, I need to work out the integral from 0, which is my bottom, right, the lower end of my range, to some variable in between. What if I go all the way to pi? What if I find the integral from 0 to pi? What happens?
You get 1.
I get 1. Not real helpful, right? So I want to find what function will define the integral between 0 and some point in between 0 and pi. So instead of saying some point, let's allocate a variable. You can call it whatever you want, right? Now, traditionally, what we do is we actually integrate between 0 and y. So some value, okay? So we're going to integrate between 0 and y. The 0 comes from the lower limit of the section that we're integrating, okay? And the y is some point between 0 and pi that we don't know. We integrate a half sine x, we get a half cos x, negative a half cos x. Okay, between 0 and y. So substitute those in just like we do for an integral. And then I end up with that function there. Okay, so I'll just give you some time to absorb that, if you wish. So, I'll leave that up just so you can see it, but I'll just move back over here. So this is now going to be the integral when x is less, when x is less than 0, can you still see that? Yes, you can, good, okay. When 0 is between, when x is between 0 and pi, then this is my function. I'll show you this in a second, okay. And I'm going to replace that now with an x. Okay, I just introduced a variable over here just so I have a value, okay? So now it's back to x because I could have called this anything I wanted. I could have called this M, I could have called it anything. I didn't want to call it X because that tends to get a bit confusing. But I could have, wouldn't have mattered, okay? If I had have, then I would have had an X there, then I would have had an X here, and then just in the past, people have gone, how do you integrate X and have an X, and there shouldn't be an X left, and blah, blah, blah. So it's all the same, all right? So it doesn't actually matter what variable you choose, okay? And then I've got 0 for X greater than pi. So that's my cumulative distribution function. Now, what does that look like? So here's a graph that I prepared earlier. Okay, so you can see the red line, and that's my y equals a half sine x graph. Okay, so between 0 and pi, and we've got that nice sine curve of the distribution. Okay, now this is the cumulative distribution function. Notice it goes, notice it goes up to 1, right? And this is the graph of a half 1 minus cos x. Okay? And we get that value. If you think about how the areas are increasing, so if you think about this graph here for a moment, as we work our way along the red graph, you can see that it's getting fatter, which means that as I work my way along x, the area as I get close to the middle gets bigger quicker. Right? And as I come down this side, the area is continuing to get bigger, so that's why it's continuing to go up, because I remember I'm going from here to where the W, right? But it's going up at a lower rate because it's getting narrower here, so it's starting to tail off again. So that's typically the shape you get for cumulative distribution graph. And so what's the significance of that? Well, if I go back to a problem that I've got over here, right? So what's the problem with x is less than or equal to pi and 2? Well, basically, as long as I'm between that value, less than pi and 2, I can just substitute that value straight into this function. Whoops. So what's that equal to? What's the cos of pi and 2? Cos of 90. 0. So I've got a half of 1 minus 0. So what's a half of 0? Half of 1, sorry. A half. Look at my graph. The next is pi and 2. Half. So the purpose of that function is I can plug values straight into that equation and it'll give me my probability for that area. Okay? The second one is between 1/4 and 3/4. How might I do that? Yeah. We can put the two values in and subtract them. So you can do that value, because that gives you the area up to pi and 4. Then you can do the area up to 3 pi and 4. And then you subtract those two. So cos of pi and 4. Okay, here's a test. What's the cos of pi and 4? You don't have to do it off the top of your head, but how would you work it out without a calculator? Cos of pi and 4. Triangles. Everyone's favourite. Okay, so what other... Yeah, it is. Okay, so which triangle? Obviously it's the pi and 4 triangle. Are we all okay with that? It's a pi and 4 triangle. Yep. Okay, so what are the sides in a pi and 4 triangle? 1, 1, root 2. Yep. So what's the cos of pi and 4? 1 and root 2. Is that okay with everyone? Don't sound convinced. Okay, now you probably will get this in a tech-free question. This is a tech-free type question. So what about the cos of 3 pi on 4? Now, we haven't done this in a while. So right now, how would I just work out that bit there? By the way, this isn't 1 on root 2. I shouldn't have done that. Yes, it is the cast rule. So it's going to be 1/2 1 minus 1 on root 2. So let's just leave it like that for the moment, okay? So cos of 3 pi on 4. Okay, what quadrant is 3 pi on 4 in? Second quadrant, right? It's up here. Okay? So it's still going to be 1 on root 2, because it's just whether it's positive or negative 1 on root 2. So up in that quadrant is cos positive or negative? It's negative, right? Cast rule, or the only American sexy tennis courts, or whatever the hell it is, right? What is it?
Sexy American tennis.
Thank you. I knew it was those words, just not in that order, right?
You had the order right there.
Did I? Okay. So it's going to be, so that value is minus 1 on root 2. It's the same ratio, it's just in a negative because it's in that quadrant. So this is going to be 1/2, 1 plus, exactly, 1 minus a negative is 1 plus, 1 on root 2. Okay, so then we have to subtract them. So it's going to be, I'm running out of space, that's why I'm taking this time. So it's going to be 1/2, 1 plus 1 on root 2, minus 1/2, 1 minus 1 on root 2. Does that look right? They get a common factor of 1/2. We've got 1 minus 1 and 1 on root 2 plus 1 on root 2, which is 2 on root 2, and 1/2 times 2 on root 2 is 1 on root 2. Yes, that's right. Yeah. So 1 on root 2, what's that as a decimal? So what's 1 on root 2 as a decimal? Yep. So what is it? Not after you do this off the top of your head. God, not that sadistic. It's 0.707, I think. 0.707. So about 0.7, right? So if we go back to our graph, does that look reasonable? Okay. So first of all, if I look at my values for, so pi on 4 is there, and 3 pi on 4 is there. So basically I'm taking that value there and subtracting that value there. Okay, now, obviously I don't know what those are. I can click on it and work it out, and then I find the area, or I'm finding the area under the red. Is that red or is that red?
That's red.
Yep. Okay. So I'm finding that area there. That's the alternative. So I could integrate between the two and get the same outcome. Okay. So I just wanted to show you that because I didn't think we did it much when we did it, and I wanted to just run by that with you. Okay. So, as I said, if you want to review that sort of thing, I didn't do the last one, but I think you guys can have a go at that one yourself in a moment. I'll put the solution up shortly. But that was all done when we did, and I think I left this one for you to do when I wasn't here, from memory, okay? Because there's no, there's not. There's a video somewhere. There's a video on this one somewhere. So anyway, I think I'm pretty sure I left that one with you when I wasn't here to do. So that's why I wanted to run through it today. Okay, so let's leave that alone for a bit. Let's try another question. Well, there's two questions. I'll probably squeeze them both on.